In this video, we're going to briefly recall summation notation and then talk about some of the formulas used to compute area under curves. So first, recall the following notation. So there is a Greek letter. It looks like this. So something like this. And it's called sigma. Okay, and so sometimes we put a little I here. And this is equal to 1. And then we go to n. And here we have a sub I. And so how this works is you start at the number here at the bottom. You start at 1. So you plug in 1. And this symbol, when you see it, it means you add. So plus. Then you plug in 2. And then again, you add. So plus. And then you plug in 3. And then you add, etc. And you keep adding. And the very last number you plug in is the top number, so n. So a sub n. So this is called summation notation. Several of these things have names. So I here is called the index of summation. Index of summation. Typically people like to use I, j, and k for the index. A sub I is called the ith term. Ith term. So a sub 1 would be the first term. A sub 2 would be the second term. A sub 3 would be the third term. A sub n would be the nth term. The numbers 1 and n, these are called the bounds. So bounds. Bounds of the summation are just the bounds. 1 is the lower bound and n is the upper bound. So there are some formulas. Before we look at the formulas, let me just do a simple example over here of how the summation notation works. So say we had the sum as I runs from 1 to 3 of 2i. So in this case, the first number you would plug in is 1. Right? So you'd plug in the 1 for the I, so you'd get 2 times 1. And the symbol means you add, and then you plug in 2, so 2 times 2. And the symbol means you add, so then you plug in 3, so you get 2 times 3. And you stop at 3. 3 is the upper bound, right? And 1 is the lower bound. So this would be 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. So you get 2 plus 4, which is 6. 6 plus 6 is equal to 12. So this summation is equal to 12. Now, in our area problems, what's going to happen is we're not going to have a number here usually. We're going to have a variable like n. And so we'll need to somehow resolve these sums, right? We'll need to get rid of the summation notation in order to take a limit. So the following formulas are very, very useful and are totally worth memorizing for that purpose. So formulas. So the first formula that we'll have is if you have a constant being added over and over again. So the finite sum as I runs from 1 to n of c. So when you plug in 1 here, you get nothing. You just get c. So it's c. And then you add again, so you just get c again. And then you add, and then you just get c. And you just get c every time you plug in the number. The last number you plug in is n, and you get c. So you have n copies of c, right? There's n of them. There's n copies of c. So you just get n times c. If that doesn't make sense, think of a simpler example. Say you had 2 plus 2 plus 2. You have 3 copies of 2. That's 3 times 2, so it's 6. If you have 2 plus 2 plus 2 plus 2, you have 4 copies of 2, so it's 4 times 2, so you get 8, etc. So here we have n copies of c, so it's nc. 2. Another useful formula is when you have the sum as I runs from 1 to n of I. And this is equal to n plus 1 all over 2. Very, very, very useful formula. Very, very useful. 3. You have the sum as I runs from 1 to n of I squared. This one's a little bit harder to remember. It's n plus 1. That part's easy. And the weird part is that it has a 2n plus 1, and it's all divided by 6. This one takes the most effort to memorize. And the very last one, there's a little trick to memorize it. It's the sum as I runs from 1 to n of I cubed. And the way I memorize it is you just square this one. So you square the n, you square the n plus 1, and then you square the 2, so you get 4. So these are the formulas that we'll need for area. Let's go ahead and do a simple example of using these formulas. So EX means example. Let's compute the sum as I runs from 1 to, I don't know, 5. No, to 50. To 50. Let's be bold. And let's do 2i plus I squared. Okay, 2i plus I squared. So to do this sum, what we typically do is we break it up, right? Properties of sums say we can break it up. So basically, you can pull out anything that doesn't have an I. So you can write this as 2 finite sum I runs from 1 to 50 of I. Okay, that's this piece here, right? That's this piece here. So basically, we took this piece and we pulled out the 2 plus, and then we have I squared, and I runs from 1 to 50. So we have 2i plus I squared. We have the same thing down here, except we pulled out the 2 and we broke them up because there's a plus sign. And so now we just use the formulas. So it's 2. So this first piece here, this piece right here, that's the formula. I'll write it again over here because you can't see it. It's I equals 1 to n, and then it's n plus 1 over 2. So in this case, our n is 50. So it's just 50, 50 plus 1, all over 2. Plus, and the other formula is still up here. This is the other one for I squared. So again, this whole thing becomes this piece here. And then you just plug in your n is 50. So it's 50, 50 plus 1, and then 2 times 50 plus 1, all over 6. And this is the part where you have to go to a calculator. So I'm going to go ahead and type this in. To make it easy for me, I'm going to cancel these 2's. That should make it a little bit easier. So it's 50 times 51. That's the first piece. So the first piece is equal to 2550. So 2550 plus, now I'm going to type in this piece into my calculator. So that's going to be 50 times 51 times, and the second piece here is 101, right? This piece here is 101, and this piece here is 51. So I'm going to type that in, 50 times 51 times 101, and then it's all divided by 6. So I got 42925. Wow, big numbers. So 42925. Then you add these numbers up, so plus 2550. So you get 45475. So 45475. And that's the final answer. That's it. Hi everyone. In this video we're going to define Riemann sums, definite integrals, and then I'll give you the formula to find the area under a curve. Before we do that, let me just tell you what a Riemann sum is intuitively. So let me draw a picture here. So this is the y-axis, and this is the x-axis. And say we have a function f, goes from here to here. Okay, and this is a, and this is b. Okay, so we have some function. And now I'm going to draw a bunch of random rectangles. So I'm going to draw a rectangle here. I'll draw a rectangle here. Okay, I'll draw a rectangle here. Okay, I'll draw a rectangle here. It's a big rectangle. I'll go ahead and draw a little skinny rectangle here. I'll draw one here. I'll draw one here. So I have a graph, and I just drew a bunch of random rectangles. Okay, if you add up the areas of all of these rectangles, you get a Riemann sum. So a Riemann sum, basically all you do is you take a graph, you draw a bunch of rectangles, and you add up their areas. That's a Riemann sum. The catch is it can be any random rectangles, right? So you can't specify what they are. So let's go through the formal construction of the definite integral so you see how intense this actually is. It's really, really cool. So we'll start by having a function f, and it's defined on AB. So f is defined on AB. Okay, so that's our A and our B, just like in our picture above. And capital delta, I believe this is the capital Greek letter delta. There's another delta, I think it's lowercase. I'm not positive, but I'm pretty sure. This is a partition. Partition of AB. Given by. So a partition is just a bunch of numbers that break up an interval, right? So our partition in the picture above, let me scroll up so you can see it. In the picture above, our partition is these dots here, which I'm about to draw. That's our partition, those random numbers there that we picked to break up the interval. Okay, that's our partition. So here, we're going to give them names. So the first number, notice here it's A in this picture. So I'll say it's A, and we'll call that x sub 0. That's less than the next one, which is x sub 1. So maybe this is x sub 1 in our picture. Less than ... less than x sub n, and we'll call that b. So I'm going to go back to our picture and just call this x sub n and x sub 0 just for added clarity, and this would be x sub 2, etc. So we're taking an interval and we're just breaking it up randomly. So taking an interval and randomly breaking it up. We don't know what these numbers are. Where delta x sub I is the width of the ith subinterval, is the width of the ith subinterval. So in our picture, this here is delta x sub I. They're all different in our picture, or some of them might be close to the same, but they don't necessarily have to be the same. So in our picture, it's the width of the rectangle, right? We haven't formed the rectangle yet down here in our description, but we will. Now, if c sub I is any, I'm going to underline this, this is key, is any point, so any number in the ith subinterval, so you just basically pick a random number in the subinterval. So like, for example, let me scroll up so you could see a little bit better. So like here, maybe here, this is my c sub I, right? That's my c sub I right there. And that what happens is we're going to plug that into the function to get the y value here, f of c sub I. You see, so when you plug in c sub I into the function, that'll give us f of c sub I, and that will give us the height of the rectangle, which you'll see shortly. So if c sub I is any point in the ith subinterval, then the sum so the sum here, we have a sum. The sum goes from I equals 1 to n. And it's the sum of the areas of the rectangle. So it's the height, which we said was f of c sub I, times the width of the rectangle, which is delta x sub I. So this is the Riemann sum of f for the partition delta. So again, we take a bunch of random rectangles and we add up their areas, and we call that a Riemann sum. All of this is just a formal way of saying all that. So what is an integral? So here's where it gets really crazy. Okay, so what is the definite integral? That's what we're defining. So if each, just a random comment, if each subinterval is of equal width, so if they're all the same width, the partition is called regular. So the partition, we can't assume that, but it's important to know it. So the partition is called regular. And in this case, we don't need delta x sub I, we just have delta x, and that's b minus a over n. So in actual calculus problems, when you do these problems, you use this formula, which I'll write down again in a little while. You assume it's regular, right? Because you assume that you can find the answer, so you can use any partition you want. So that's what that would be. So now we're going to define something. We're going to let this symbol here, so like these double bars around the partition, we're going to say this is the norm of delta. And what is this? This is the width of the largest subinterval. Okay, of the largest subinterval. It's the width of the biggest one. Okay, the width of the largest subinterval. Notice if the partition is regular, they're all the same. So if the partition is regular, in the regular case, you would get that the norm is equal to delta x, which is equal to b minus a over n. That's kind of cool to notice, and we'll come back to that. All right, so here's the key. So if we take the limit as the width of the largest subinterval goes to 0 of the finite sum of the areas of these random rectangles, okay? And if this limit exists, so if this limit exists, we say the function is integrable. We say f is integrable on AB. Okay, we say it's integrable on AB, and the limit, right, since it exists, is, so I'll write it again, we have the limit, and I'll explain why intuitively this is the case as well in a second. The limit, as the norm goes to 0, of the finite sum, as I runs from 1 to n, of f of c sub I times delta x sub I. We're going to say it's equal to what's called the definite integral of our function. So the definite integral of f of x with respect to x from a to b. That's what it's called. It's called the definite integral of f from a to b. Okay, and in the case if f is non-negative, so if it's greater than or equal to 0 on AB, then the area under the curve will be this. Okay, that will be the area under the curve. Before I give you the formula for the area, let me just explain why this should make sense, because it probably doesn't yet, or might not. So if you have a bunch of rectangles, right, and you're trying to find the area, you're either going to get an under approximation or an over approximation. So if you let the width of the biggest rectangle go to 0, what's going to happen is you're going to get smaller and smaller rectangles, right? You'll get more rectangles. So eventually you have infinitely many rectangles, and they cover the area, and so you get the area. So because if the biggest rectangle in width goes to 0, all the other ones must go to 0 too. So you get like tons of really super skinny rectangles, and you get all of the area. Notice in the case where it's regular, so if all of the subintervals have equal width, we just got delta x, which was b minus a over n. So if this goes to 0, then n goes to infinity. So if you like, you can replace this with n going to infinity in your mind, and that way you can actually compute it. In fact, in the problems, that's what we do, right? We let n go to infinity, and the reason we do is because we assume a regular partition. So the formula that we tend to use in problems is the following. So the area under the graph from a to b, we say it's the limit as n goes to infinity of the finite sum as I runs from 1 to n of f of c sub I times delta x. Okay, and so delta x here is b minus a over n. And notice this agrees with our definition up here, right? If the length of the largest subinterval goes to 0 and delta x is equal to this, that means n must get really, really big, so n goes to infinity. That lets us actually do the computation mathematically. And c sub I, well, before it was any number in the interval, so we force it to be a plus I delta x, so we can actually compute it. This is the right endpoint. So this is the formula we use to find area. So definitely not going to do an example in this video because they take like 10 minutes. They're really long. You have to work through all of this. But I hope this video was helpful. And yeah, that's it. This video, we're going to find the area under the graph of this function from -2 to 2 using the limit process. So this is a long process, but it's not too bad if you just go slow and you take your time. So let me give you the formula for area and then we'll slowly go through it. So the area is equal to the limit as n goes to infinity of the sum as I runs from 1 to n of f of c sub I times delta x. So this is the formula for area, okay? This is also equal to something called the definite integral from -2 to 2 of 4 minus x squared dx. So this is the easy way to do it. Once you know something called the fundamental theorem of calculus, you can just work this out really quickly. You can put this into, like, Wolfram Alpha or a calculator, and it will give you the answer. So we're basically doing things the long way. It's kind of like when you first learn derivatives. You have that definition with the f of x plus h minus f of x. This is the same thing, except it's for intervals. Let's draw a picture of what we're actually finding, and that's going to let us take a really cheap shortcut. So this is an upside down parabola. And it goes from -2 to 2. It looks like this. And so we're finding the area under this parabola. So notice that we're going from -2 to 2. So instead of doing that, what we can do is we can just find this area and then multiply the answer by 2, right? Because these areas are the same. So instead of going from -2 to 2, let's cheat. Let's go from 0 to 2. And at the very end of the problem, we're going to multiply our answer by 2. It's just a really nice shortcut we can take. Again, we're trying to find the area of this entire piece, so we're just going to find this area and then multiply the answer by 2. Okay, so let's go ahead and work it out. So delta x, what is that? So delta x is equal to b minus a over n. So b here is going to be the 2, and a is going to be the 0. So this will be 2 minus 0 over n. So this is just 2 over n. So delta x is 2 over n. So that's an accomplishment. That's important. I'm going to put that in a little box. So why did I do that first? Just because we're trying to come up with this. So I like to do it in steps. So first we find delta x. C sub I is another formula. It's a plus I delta x. So a is 0. This is why I did this. It makes it so much easier when a is 0. So c sub I, so it's gone because it's 0. So you just get I times 2 over n. These problems are pretty fun. I actually haven't done one of these in a long time. So c sub I is equal to 2i over n. So I'm going to put that in a little box. That is an accomplishment. So now we got to work out f of c sub I. So by the way, this is our f of x. Right, y is equal to f of x. So f of c sub I is f of 2i over n. So we have 2i over n. So that's equal to, well, it'll just be 4 minus x squared. So 4 minus this thing here squared. So 2i over n squared. So this is 4 minus, so you just get 4i squared over n squared. Going kind of fast. Let me go ahead and just rewrite it here. This is f of 2i over n. Okay, so that's our f of c sub I. It's hard to read that. F of 2i over n. So that's this piece. So this is this piece here. Let's go ahead and write the summation sign. So we have the summation as I runs from 1 to n of this piece.
So we work that out. It's this. It's 4 minus 4i squared over n squared. So 4i squared over n squared. And then we have our delta x. What was delta x? The power of boxes. We put it in a box. It's 2 over n. Let me pause here and just go over what we did. So the question is to find the area under the graph of this function. We drew a picture of the graph. We decided, hey, instead of finding the whole area, let's find half of it and multiply the answer by 2. We did that because it makes the a 0. It makes it really nice. So step 1, you find your delta x. It's b minus a over n. You get 2 over n. So really important to know this formula. Then you find c sub I. It's a plus I delta x. A is 0, so it goes away. So we have our c sub I. Then you take your c sub I and you plug it into your function. So we did that here. And now we're going to write this summation sign. Notice I didn't write the limit yet. I like to wait to the very, very end of the problem, then I write the limit sign. Because once you write the limit, you have to keep writing it in order for the, otherwise it's wrong. So I like to be really lazy and wait to the very end and then just take the limit at the end. Next step. So basically now we're going to multiply this times this, okay? And anything that doesn't have an I, you can pull it out. So watch. So 2 over n times 4. So 2 times 4 is 8. So it's 8 over n. And we can pull it all out. So we have I equals 1 to n. And then we have a 1 here. See, 2 times 4 is 8. And then you have the n. And then minus 2 times 4 is 8. So you get 8. N times n squared is n cubed. So you get n cubed. And again, if it doesn't have an I, just pull it out. Okay, so this is I squared. So super key. You can show a million steps here, but it's just not worth it. It's always better just to do it in one step. So this times this is 8. So 2 over n times 4 is 8 over n. You pull it out because there's no I. So you're left with the 1, right? Because if you multiply this times this, you get 8 over n. 2 over n times this, 2 times 4 is 8. Boom, there it is. N times n squared is n cubed. Boom, there it is. All right, so this is going to be equal to 8 over n. This is n. Whenever you have 1, and you're adding it to itself over and over again, you just get n. So this is just n, always, right? Minus 8 over n cubed. This is a formula, okay? It's n, 2n plus 1, sorry, n, n plus 1, 2n plus 1 over 6, right? So it's a really annoying formula to memorize. So it's n plus 1, 2n plus 1, and it's all over 6. That's what this is. Now we're ready to take the limit. I know these cancel, but I'll write that later. So we've used our formulas, so now we have to take the limit, and that's almost the answer. So the limit, as n goes to infinity, I'll go ahead and cancel this, of 8 minus 8 over n cubed. And then we have n plus 1, 2n plus 1, and it's all over 6. Okay. So what is this going to be? Well, the 8 is just 8 no matter what, right? Because it's just constant, so it's 8. Here, notice it's n cubed. It's n cubed over n cubed. So you just want the ratio of the leading coefficient. So just, what's the highest coefficient? The coefficient of the biggest degree term. So it'll be 8 times 2 here, because 8 times 2 is 16. Remember, it's the limit we're taking, so we only care about the highest degree terms. So 16 over 6. So that's going to be 8 minus 16 over 6 is 8 over 3. Okay, but that's not the final answer. Let's go ahead and combine these. 8, how do you write 8 as a number over 3? Wouldn't that be 24 over 3? Yeah, because 3 times 8 is 24. So this is equal to 24 over 3. Yeah, because that's the same as 8. Minus 8 over 3. And then 24 minus 8 is 16. It'd be really bad if I mess up here. But that's not the answer, because we have to multiply by 2. So because we only found half the area, so 2 times that would give us 32 over 3. This is like a medium difficulty problem. We made it easy by making that a 0. Let's think about the complications that if we wouldn't have done that. If we wouldn't have done that, you would have had a 2 here, right? Because this would have been 2. Or sorry, negative 2. And then when you plug it in here, you would end up with like negative 2 plus, something like this. I think you would get something like this, yeah. And then you'd have to square that. So it would have been a lot more work. So nice shortcut that we took. I hope this video has been helpful. Take care.
this problem, we're going to evaluate this definite integral using the limit process. So we're going to do it the long way. So before we do it, let me just briefly recall the formulas that we're going to be using in order to do this problem. So recall that if you have the integral from a to b of f of x with respect to x, you can do the following. This is equal to the limit as n approaches infinity of the finite sum as I runs from 1 to n of f of, and I'll use c sub I, some books use x sub I, and then delta x. And for c sub I, we're going to choose these endpoints here, a plus I delta x. And there's different ways to do this. This is just one way. And then for delta x, we're just going to use b minus a over n. So this is the width of the subintervals. We're going to choose a partition such that each subinterval is of equal width. It's called a regular partition, just extra knowledge. Okay, so this is what we need to do. So we need to work our way up to this, right? And then at the very end, we'll take the limit. So we just do it one step at a time. So I really think it helps to write down the formula every time you do one of these and just go really slow. So first, let's identify a and b in this problem. So it looks like a is the bottom number. So a is 1, success, right? So, and b is 4. So we've got some progress done. So, and now we can find out delta x, because we can't really get c sub I until we get delta x, right? Because you see it appears here in the formula. So delta x is b minus a over n. So delta x is going to be 4 minus 1 over n. And you might say, what's n? It's just n. So it's 3 over n. So delta x is equal to 3 over n. And I'm going to put this in a box just because, you know, it just makes it easier to identify. Also, if you're taking a class, like if you're doing this for like school or something, you know, if you're taking a test or something, it just helps. Like, you know, the person who's grading your work be like, oh yeah, they found delta x. You know, they know how to do that. So, and then c sub I is a plus I delta x. So a is 1 plus I, and then delta x was 3 over n. And that looks really funny, so I'm just going to write it like this. C sub I is equal to 1 plus 3i over n. And just again, just to add some clarity and to keep me from going way too fast, we have c sub I equals 1 plus 3i over n. Plus, if you go too fast, you make mistakes. All right, so now we need to figure out this piece up here. So we've got the delta x, that's good. We need f of c sub I. So this is our f of x, this whole thing here. Without the dx, obviously, just this function. So now we need to plug this into f of x, and this is where people sometimes mess up. So f of c sub I, now I'm not going to put c sub I, I'm just going to put 1 plus 3i over n, because it's the same thing, right? So just like that. Right, this is f of c sub I right here. This is the c sub I. And then you just replace each copy of x with 1 plus 3i over n. So this is 1 plus 3i over n, and that's squared, plus, and then 2, and then it's 1 plus 3i over n, and then minus 5. And this is where rushing sometimes, like, it's really easy to mess up. I've messed up, and it's just, you know, easy mistakes, right? That's why it's good to have everything in boxes. All right, so to multiply this out, there is a formula. I'm going to use a different color here. If you have a plus b quantity squared, I think of a as the first and b as the second. So you square the first, and then you multiply the a and the b and you double them, and you square the last. That's how I memorize the formula in my head. So this is, or I just have it memorized too, like this, but it's a nice way to think about it when you're working it this way, because there's no a and b here. So you square the first one, plus you multiply these two. So 1 times 3i over n, that's just 3i over n, and then you double it. So times 2 will give you 6i over n. And then you square the last one. So you have to square the 3, so you get 9. You square the I, so you get I squared. You square the n, so you get n squared. And I just had this thought, so I'll share it. It's not an imaginary unit, right? It's not going to be -1, right? It's a variable. So I've seen people do that. It happens. So plus 2 times 1 is 2. And then 2 times this will be 6i over n. And then we have the -5 here that's hanging out. Okay, so let's combine like terms. And just as a formality, I'm going to put all of the terms of like highest degree first. So like the I squared terms first. So I'm going to put that one first. So this would be n I squared, just to give myself some structure so it looks a little bit better for me. 6i over n plus 6i over n is 12i over n. And then we have a bunch of numbers we have to add. This is where it's really easy to mess up. So 1 plus 2 is 3. 3 minus 5 is -2. Wow, I hope I did that right. That's like, yeah, let's do it backwards. -5 plus 2 is -3, plus 1 is -2. Yep, that checks. So this is f of, I'm going to put c sub I now, just to really make the point. So this is f of c sub I right here. I'm going to put it in a box as well, right? Because this is c sub I here. So now you see we have everything we need in these nice little boxes, right? We've got delta x, we've got c sub I, we've got f of c sub I. So now we can start filling it in. So I'm going to go ahead and write this piece now. I'm going to wait to the very end to write the limit. And the reason is I'm sure you know, once you write the limit sign, you have to keep writing that limit sign in every step until you actually take the limit. So let's go ahead and write out the formula. So we have the finite sum as I runs from 1 to n. It's really important to write it all out like this. I think it really helps. F of c sub I delta x. So this is equal to the finite sum. I might have to try to write a little smaller here. I don't know if that's possible though. So f of c sub I is this piece here. So basically we just replace it. So parentheses 9 I squared over n squared plus 12i over n, 12i over n, and then minus 2. And then we have delta x. Well, what's delta x? Ah, it's in a box, right? The beauty of boxes, now it's circled. It's in a circle box. 3 over n. Okay, so this next step is a step where you can show a gazillion steps, but honestly, it's better to skip some steps here. It's easier. So watch this. I'm going to take this. I'm going to switch colors here. I'll go back to yellow. And we're just going to distribute. So we're going to do this times this. And everything that doesn't have an I, we're going to pull it out of the sum, okay? So 3 times 9 is 27. I'm going to write it over here. Okay. N times n squared is n cubed, right? Because the sum depends on I. It's the index of the summation. So anything else you can pull out. So this is the sum as I runs from 1 to n, and we're left with simply I squared, right? And then that's on purpose. I wanted to have that there so we can use the formula for I squared, right? Because we have that formula and we can use it. So super, super useful. Again, 3 times 9 is 27. Okay, so no worries there. And then n times n squared is n cubed, right? N cubed. Okay, the next one is a plus. And then 3 times 12 is 36, so that doesn't have an I, so we can pull it out. And then n times n is n squared. And then we have the sum as I runs from 1 to n. Once you do one of these on your own, like without watching the video, like you're going to be a monster. And then this is I. And that looks okay. And minus, it's really easy to mess up. There's no i's here, so 3 times 2 is 6. Over n, and then here we have I going from 1 to n, and this is just the number 1, right? Just the number 1 there. All right, so now we can apply the formulas. I'm just going to go ahead and apply them. So this piece hangs out, 27 over n cubed. This piece here, this is a formula. Okay, this formula is n plus 1, 2n plus 1, all divided by 6. Okay, so it's a little bit weird. I remember having a really hard time memorizing this one. How do I memorize it? I just know it's that. I mean, I don't really have a nice way. It's very similar to this one. So you'll look. So this is 36 over n squared. This one is the easy one, right? This one is n plus 1 over 2. So I squared has the n and the n plus 1. That part's easy because this one has it. But then it has that 2n plus 1 and the weird 6. And that's always the part that threw me off with memorizing it. For some reason, I had a hard time memorizing that. But once you memorize it, you got it. Minus 6 over n. And then this is just n, right? This is just n. I should have emphasized that this here is this here, right? That's what this is. And then this here is this here. And this here is the n. Right? So little arrows pointing to what is what. Let's go ahead and take the limit and we're done, right? So the limit. Oh, let's be really pro. Let's write the original question again. Actually, I'll have it written down somewhere. Maybe I don't. So what was it? It was x squared plus 2x minus 5 from 1 to 4. So x squared plus 2x minus 5. So x squared plus 2x minus 5 dx, right, when we're going from 1 to 4. And this is the limit as n goes to infinity. I'm going to use a different color here. Go to orange. So I'm going to go ahead and write it again. I'm not going to simplify anything. I'm going to put this in parentheses. 27 over n cubed. n plus 1. 2n plus 1. All over 6. My handwriting is deteriorating. These problems are long. Plus 36 over n squared. Then we have n plus 1 over 2 minus, okay, I'm going to go ahead and cancel it. I can't take it. 6. All right. And this is equal to, so here on the bottom, the degree is 3. But here it's n. It's also 3. You see you have n times n times n, so you get n cubed. So it's just going to be the ratio of the leading coefficients. So it'll be 27 times 2, which is 54, over 6. Okay, that's really sneaky, right? You do have to multiply the 27 here and the 2. Okay, so plus, and then this is 36n squared over 2n squared. So it's just 36 over 2. And then minus 6. So this is equal to 54 over 6 is 9 plus, right, because 6 times 9 is 54, plus 18, right, 18 times 2 is 36, minus 6. This is equal to 9 plus 18 is where we're going to fail. This is 27 minus 6, right? Yeah. Which is 21. Wow, brain failure. Let's do that a different way, just to make sure we're not completely messing up here. So 18 minus 6 is 12, and then you have 9, you add it to that, and it's 21. Wow, the struggle is real. So 21 is the answer. So that's it. That would be the answer to the question. I hope this video has been helpful, and remember, just take it one step at a time, right? Start by writing down the formulas, circle stuff, and then just carefully go through it. Good luck.
Hello, in this problem we're going to find the area using the limit definition. Our function is y equals 27 minus x cubed, and we're going to find the area under the graph from 1 to 3. So to do that, we're going to use a bunch of formulas. So solution. Let me show you what the integral would look like just for fun, just to show you. It only takes a second. So to find the area here, this is the same thing as the integral of 27 minus x cubed dx, and we're going from 1 to 3. So you can use very simple formulas to come up with the answer, but this problem wants us to do it with the limit definition. So this is the formula we're going to use. This is going to give us the area. It's the limit as n approaches infinity of the finite sum as I runs from 1 to n of f of c sub I times delta x. So this is going to give us the area. So in this particular problem, the f of x is this right here. So our f of x is 27 minus x cubed.
Okay, they call it y, but that's going to be our f of x. All right, and then so what is everything else? So delta x is going to be equal to b minus a over n, so we need that formula. I'll put it in a box because that's something you'll need. And also c sub I, we're going to use this one. It's a plus I delta x. That's going to be our c sub I that we're going to use. Okay, and equipped with these things, we should be able to do this problem. So in this particular problem, a is 1 and b is 3. I should also mention that this problem is very messy and I haven't done it yet, so I'm going to do my best to not mess up. All right, it's very easy to mess up. So first we have to find delta x, because you see it shows up here in the c sub I, so we can't find it without the delta x. That's pretty easy though, right? So delta x is b minus a, so it's 3 minus 1 over n. Super easy, so 2 over n. Good stuff. So delta x is 2 over n. Delta x is equal to 2 over n. That's good. C sub I is a plus I delta x. So a is 1, so it's 1 plus I times delta x. So I times 2 over n. That's simply going to be C sub I equals 1 plus 2i over n. Okay, so we've got delta x, we've got C sub I, so now we somehow have to work this out. Let's first focus on finding this, f of C sub I. Once we have this is the hardest part. We'll plug it in and then work out the sum. So recall that f of x in this problem was 27 minus x cubed. So we want f of C sub I. That's the same thing as saying f of 1 plus 2i over n, which is equal to 27 minus parentheses 1 plus 2i over n cubed. Okay, so now we have to work this out, which is a bit of a mess in some sense. So you could just multiply it out. I'm going to take another approach. Recall the very powerful triangle of Blaise's triangle. Actually, it's Pascal. His first name was Blaise. I think it's how you say it. Pascal's triangle or Blaise's triangle. So you write a 1, and then you put 1s on the sides. 1 plus 1 is 2. You put 1s on the sides. 1 plus 2 is 3. 2 plus 1 is 3, and you put 1s on the sides. This is row 0. This is row 1. This is row 2. This is row 3. You start counting at 0. Again, 1, 1, 1. 1 plus 1 is 2. And then 1s on the sides. 1 plus 2 is 3. 2 plus 1 is 3. You put 1s on the sides. I stop here because there's a 3 here. These are the coefficients, okay? And so this tells you a formula for this. So basically the formula, it's a cubed plus 3. So it's 1a cubed, 3. And then the a goes down in exponents. So it's a squared. And the b goes up. So b to the 1 plus 3a, b squared plus b cubed. So the a's decrease in power. 3, 2, 1, 0. The b's increase in power. B to the 0, it's not there. B to the 1, b to the 2, b to the 3. Very powerful, worth memorizing. Again, 3, 2, 1, 0, 0, 1, 2, 3. So now we're going to apply it to this. So this is equal to 27 minus parentheses. So a cubed, a is 1. So it's 1. Right, so here a is 1, b is 2i over n. And then it's plus 3a squared b. So it's plus 3. A squared is 1, so I won't write it. B is 2i over n. Plus 3. A is 1. B squared is going to be this squared here. So it'll be 4i squared over n squared. And the last one is b cubed, so plus 8i cubed n cubed. Right? So very powerful technique. And I actually have 1331 memorized, and I have this memorized already, so it's not hard for me. But if you don't know this, it's tough because you have to know the triangle. I'm going to do the triangle one more time over here. 1, 1, 1. 1 plus 1 is 2, 1, 1. 1 plus 2 is 3, 2 plus 1 is 3, 1, 1. 0, 1, 2, 3. Those are your coefficients. You start with 1, and then it's a cubed, and then b to the 0, so you don't write it, plus a squared, plus 3a squared, b to the 1, plus 3ab squared, plus b cubed. So notice the exponents go down on the a, 3, 2, 1, 0. They go up on the b, 0, 1, 2, 3. The coefficients are 1, 3, 3, 1. Let me go ahead and delete all of this and get it out of the way so we don't have it here anymore. But same deal. So this is equal to 27 minus 1. Right, we'll distribute the minus 1 here. 6i over n, so minus 6i over n. Minus 3 times 4 is 12, so 12i squared over n squared. And then minus 8i cubed over n cubed. Ridiculous, right? Ridiculous. A little bit of simplification here. We can subtract the 27 and the 1. So this is equal to 26 minus 6i over n minus 12i squared over n squared minus 8i cubed over n cubed. All right, so all of this is what? This was f of c sub I, right? F of c sub I. And let's go ahead and write down, what else do we need? We need our delta x. That was 2 over n. That was from before. And so now let's go ahead and write down the formula for the area. So our area, which I wrote down the formula earlier, I wrote it as an integral, is equal to the limit as n approaches infinity of the finite sum. I usually write the limit at the end, but I'll write it here so you see it all together, because this problem is so messy that I feel like I don't want to get derailed from the main idea. It's f of c sub I times delta x. Okay, that was our formula. And so we've worked out f of c sub I. Okay, we've worked out delta x. So now what we're going to do is we're going to just focus on the sum, okay? And then at the very, very end, we'll come back and take the limit. So I'm going to write the sum down by itself. So the sum, as I runs from 1 to n. Okay, f of c sub I, we worked it out, so I'm going to write it out. It's 26 minus 6i over n minus 12i squared over n squared minus 8i cubed over n cubed, and then times delta x, which is 2 over n. Very messy problem. This is probably one of the messiest ones found in most textbooks that are used to teach calculus, at least in the US. I decided I should do a really messy one. So now what we're going to do is I'm going to use some super powerful math. Basically, we're going to break this up into 4 sums, and we're going to do it all in one step. It'll save us years on our life. So watch this. If it doesn't have an I, you pull it out. So watch this. 2 over n times 26, right? You multiply that. 2 times 26 is 52. So it's 52 over n, and then we're pulling it out, and it's going to leave us with a 1. Then minus 2 over n times this. That's going to be 12. And then n times n is n squared. And then we have the sum of the i's. Really beautiful. Really cool. 2 times negative 12 is negative 24. This is just how I do it. I don't know how other people do it. N times n squared is n cubed. And then here we have the sum. It's just so much cleaner to do it like this, because you can spend hours, or not hours, but you can spend a long time, writing this a million times. It's a lot of summation symbols. You want to make it as easy as possible for yourself. And then this times this will be 16. So minus 16. N to the 4th, right? Because n times n cubed is n to the 4th. And we're left with the I cubes. I cubed. Beautiful. So we've basically worked out the sum. So all we have to do now is take the limit. But
we still have these sums here. So let's go ahead and apply the formulas. And this is like the ultimate problem because it requires all the formulas that are typically found in the calculus book. So every single formula is used. So this is 52 over n. So this one here, this is just going to be n because you're just adding 1 to itself over and over n times. So n minus 12 over n squared. This one here is a very popular formula. It's n plus 1 over 2 minus 24 over n cubed. This one is n plus 1, 2n plus 1 over 6. This is the worst one. I always had a really hard time with this one. And then minus 16 over n to the 4th. This one's n squared, n plus 1 squared over 4. I actually just proved this 2 days ago. I did an induction proof on this to show that this is equal to this. You can prove these formulas, by the way, using the principle of mathematical induction. I've done all of these. And yeah, there's actually one for a 4 here, but it gets really messy there. So that's typically not found in most books because it just gets a little bit out of control. It's kind of like the cubic formula. It's just a little bit crazy. So now we just have to take the limit. So I guess I can write the limit sign here and cheat. So let me do that. So let me just say then. So like a transitory, is that the right word? I don't know. Limit as n goes to infinity. Now we're going to add the limit, and now we'll take the limit. So this is just going to be 52. What about here? So what we're going to do is we're going to focus on leading coefficients. So in the numerator, the term of highest degree is 12n squared. In the denominator, it's 2n squared. Whenever the degrees match and you're taking a limit as n goes to infinity, the answer is always the ratio of the leading coefficients, and that's because the growth rate is the same, and all the other terms of smaller degree are inconsequential because n is growing without bounds, so we only care about the higher order terms. So it'll be 12 over 2, which is 6, but I'll leave it as 12 over 2. Oh, it's not plus. Look at that. Minus 12 over 2 minus, here it's 24 n, so it's n, so n cubed, but it's 24 times 2, so it's 48 n cubed, and on the bottom it's 6n cubed, so it's 48 over 8, right? Because 2 times 24 is 48. You got to be really careful there. Very commonplace that people mess up. And then minus, this is going to be 16. This is also squared, so 16 n to the 4th over 4 n to the 4th. So it'll just be 16 over 4 because the degrees are the same. So let's see what this is going to be. This is 52 minus 6 minus 6, right? 6 times 8 is 48 minus 4. Not mess up here. That'd be really bad. This is equal to 52. Oh, let's see. Negative minus 16. Minus 16. I think this is 34. Yeah, it's 34. Right? 34? Or no, is it 34? No, it's not 34. Oh, brain death. 52 minus 16. Old school. 12. Borrow a 10. 12 times 6 is 6. 36. Yeah, 36. That's better. 36 is the answer. Wow. You get to the very end of this problem and you forget how to subtract numbers, but I feel like there's a mistake somewhere. I don't think that this is 100% correct. So 52. There's a 6 here. This is a 6, and so this is an 8. I knew something was off. So I made a little mistake here. So this is 48 over 6. Let me use a different color here. I'm glad I caught that. So this is 48 over 6. So this is going to become an 8. So it'll be 52 minus 6 minus 8 minus 4. So it'll be 52 minus, let's see, minus 18. Minus 18, so that's going to be 34. Right, 34 should be the final answer in this problem. Wow, really easy to mess up. So be very, very careful with problems like that. You saw how I messed up there. I put an 8 here instead of a 6. So I'm glad I caught it. And 34, let me see, let me just check here. 34 is actually the correct answer. So it is 100% correct. So be really careful. You see how easy it is to mess up in these problems. In any case, I hope this video has been helpful to you, and it's a long problem, right? Like there's no easy way. And I'm kind of glad I messed up at the end just to show you how easy it is. The most common mistake though is the multiplication here between the 24 and the 2. That's the most common mistake. Like if people make it this far, that's typically where they mess up. And I guess sometimes people, like me, will write the wrong number down. So that's also a way to mess up. I hope this has been helpful to you. Good luck.